Intra-body communication is a new communications technology for electronic devices. By sending imperceptible low-power electrical signals through the human body, nearby electronic devices can communicate. Typically, a person will carry a personal device that communicates with other devices in the person's environment to exchange access privileges, preferences, or information about the user's current task. Unlike a short-range radio, the signal is confined to a small space around the person, reducing interference from other transmitters and reducing the chances that a signal could be intercepted. We have constructed 3 prototypes. We began with the designs of similar devices created by Thomas Zimmerman at the MIT Media Lab and enhanced them to improve bandwidth and to measure the received signal strength. The transceivers measure 3 inches by 5 inches. However, a commercial product could be made much smaller using a custom chip. This work investigates the performance of these prototypes under various situations. The physical principle enabling intra-body communication is capacitive coupling. A low-frequency AC voltage placed across 2 conductive surfaces generates an electric field that produces a detectable voltage between other nearby conductive surfaces. A person in the electric field draws more field lines through their body, increasing the voltage seen by the receiver. We tested 3 different places to couple the signal to the body. A wrist coupler is probably the most natural coupler, since many people already wear watches. A belt coupler is also convenient, since many electronic devices such as cell phones and pagers are already clipped to belts. We also tested a shoe coupler because other researchers have found that the shoe performed extremely well. The transceivers are powered by 4 9-volt batteries, although a commercial design could use fewer. We chose this configuration to allow a large, precise transmit voltage swing of 20 volts without noise interference from a charge pump. A late addition to our original design regulated the supply voltage to plus and minus 12 volts. This prevents battery supply drift from affecting signal strength measurements. For devices that a user touches, we used a basic setup of 2 plates elevated on a cardboard box above a table. The cardboard box isolates the plates from conductive materials inside the table, which might otherwise affect our results. The following test shows the performance when a person touches the plates on the table that transmit the signal, and the receiver is coupled to the person using the shoe. To test the system's data transfer capabilities, we sent a byte stream of increasing counter values using a UART serial protocol. The upper trace shows the data signal transmitted at 56 kilobits per second. The received signal is shown in the lower trace. The trace fades in and out as the person moves their hand away from the transmitter. With direct contact, the signal has a bit error rate less than 0.001%. This is an improvement upon the result reported in our paper. Our transceivers contain an active rectifier circuit to measure the signal strength. The new lower trace shows the signal strength circuit's output. This value is digitized and sent over a serial line to a PC. We calibrated the value using a signal generator capable of producing frequency shift keyed signals at accurate voltages. The signal amplitude can be as low as 20 microvolts without affecting the error rate. By 17 microvolts, the error rate rises to 0.25%. By 10 microvolts, the data cannot be recovered. However, the minimum voltage depends on the decoder chip we use. Other designs or implementations for encoding data might have a different voltage minimum. We therefore report values in terms of signal strength at the receiver inputs. A complication in measuring signal strength is that test equipment is connected via a power cord to earth ground. Grounding our battery-powered transceiver connects it to the power grid, thereby improving the return path connection. When removing the grounding from the transmitter, the signal strength measured at the receiver drops noticeably. Grounding the receiver also affects the received signal strength, but it cannot be easily seen from the scope trace. To avoid these effects, the serial data is transmitted over a short-range radio link to a PC. The oscilloscope verifies that the radio does not affect the signal strength measurements. We ran tests comparing the performance of the shoe, wrist, and belt. This graph supersedes a similar graph in the paper, which had been performed on earlier electronics. The result, however, is the same. The shoe performs significantly better. Although the surface area of the belt and the shoe are comparable, the shoe performs better because of the close grounding connection between its outer plate and the floor. In fact, the signal from the belt is barely decodable, and the wrist coupler performs only slightly better. The wrist coupler is sensitive to which hand is used. With a non-coupled hand, the signal strength is reduced by a factor between 2 and 10, depending on hand orientation and coupler position. We also tested the coupler's performance on a PDA fitted with copper plates. Because of the poor grounding of the PDA, it does not perform as well. However, if the PDA grounding plate is brought near the wrist grounding plate, signal strength improves significantly. If it makes contact, the signal strength reaches its maximum value. The belt behaves similarly with its grounding plate. The signal strength can also be improved by the addition of a large conductive transmitter plate on the floor. Although this is not feasible for portable devices, infrastructure devices may be able to take advantage of it. In some circumstances, signal strength can be improved by directly touching both transmitter plates. When grasped with opposite hands, the wrist receiver sees a tenfold increase in signal strength. Touching both plates with a single hand also helps, but by a much smaller factor. The shoe actually sees a decrease in signal strength because less current reaches it. This graph summarizes these findings. The wrist and belt can perform better than shown here if the grounding plate is within a few centimeters of the device's grounding plate. One undesirable characteristic of intra-body communication is that communication is sometimes possible even when a person does not touch a device's plates. For example, the wrist coupler can communicate when the wrist is brought close to the plates of the other device. Touch-selective communication is preferable because it reduces interference, makes eavesdropping more difficult, and isolates signals of multiple people. The transmit voltage can be reduced so that communication without touch is less likely. However, exceptional situations still arise because signal strength varies significantly. The shoe is not without its problems. Received signal strength is reduced by a factor of 2 to 5 when the foot is raised. We also tested variations in plate sizes between 25 square centimeters and 200 square centimeters. Changing the touched plate size made little difference. Changing the grounded plate reduced the wrist and belt signals, but only for small plates. An important characteristic of intra-body communication is its performance when multiple people are present. We attached two transmitters to separate users, one with an increasing counter and another with a decreasing counter. The receiver was placed on the box and lit a different LED when the appropriate signal was received. Conclusions. Because of good grounding, the shoe performed significantly better than the wrist or belt. Wrist performance was marginal, and belt performance was frequently unusable. Communication can happen without touch. Touch-selective communication would be preferred for some applications, but is not yet reliable. Intra-body communication distinguishes transmitters on different people well, but more study in this area is needed to determine the effects with multiple receivers and to determine the effects of variations with different couplers.